I know it's already 11 a.m. and you're hungry, most likely, right? So let's get it done as quick as possible. Agree? Yes. Okay. Now, yeah, let me just go back to sharing my screen and let's look a little bit on what has transpired in our class yesterday. So just jump to this one. Okay. So what happened in our class yesterday? It's pretty much very simple. We looked into what computer science is and what role do we play as students and as future computer science professionals, right? And yeah, we came into the agreement that as computer science specialists or professionals, we are what? Problem solvers, okay? And we solve problems with the help of a computer, of course, which is using technology to solve problems, right? And we went into talking about the most basic way of what? Solving a problem, which is, of course, what? Writing algorithms, right? So I actually skipped this video yesterday. However, I'm going to play it. And then thereafter, we move on to you presenting the research that you actually worked on with regards to the different sorting algorithms that was actually assigned to you per group, that is, okay? So let's watch this for a bit. It's not gonna go purely.
What is an algorithm? One definition might be a set of steps to accomplish a task. You might have an algorithm for getting from home to school, for making a grilled cheese sandwich, or for finding what you're looking for in the grocery store. In computer science, an algorithm is a set of steps for a computer program to accomplish a task. Algorithms put the science in computer science, and finding good algorithms and knowing when to apply them will allow you to write interesting and important programs. Let's talk about a few famous algorithms. How does Google Hangouts transmit live video across the internet so quickly? They use audio and video compression algorithms. How does Google Maps figure out how to get from Dallas, Texas to Orlando, Florida so that you can get to Disney World? They use a route finding algorithm. How does Pixar color a 3D model of a character based on the lighting in a virtual room? They use a rendering algorithm. How does NASA choose how to arrange the solar panels on the International Space Station and when to rearrange them? They use an optimization and a scheduling algorithm. Those algorithms are more complex than our everyday algorithms, like making a grilled cheese sandwich, but they boil down to the same thing, a set of steps to accomplish a task. If you know something about existing algorithms, you can save yourself some effort and make your programs faster by applying the right one. For example, let's say that you're writing a game and you want the user to be able to play against the computer. Well, you could look at checkers games for inspiration. Computer scientists have figured out how to write checkers programs that never lose by using the Minimax search algorithm to search through the huge tree of possible moves. If your game is similar to checkers, then you might be able to use algorithms based on these techniques. If not, then knowing the limitations of those algorithms might lead you to redesign your game if it requires having a skilled computer player. It's also important to know how to design new algorithms, as well as how to analyze their correctness and efficiency. In the biological sciences, new algorithms are continually being designed for purposes like designing the molecular structures that are the core of disease-fighting drugs. In physics, algorithms simulate climate and weather patterns, and other algorithms search and analyze the vast data about stars in the universe that's collected by automated space telescopes. Across all the sciences, and even on websites like Khan Academy, efficient algorithms are needed to analyze huge data sets or to select intelligently from a vast number of possible decisions. In just about any area you might be interested, new algorithms will allow massive computational power to be harnessed to do things that people really need and care about. Now, not all algorithms are created equal. So what makes a good algorithm? The two most important criteria are that it solves the problem and that it does so efficiently. Most of the time, we want an algorithm to give us an answer that we know is always correct. Sometimes we can live with an algorithm that doesn't give us a correct answer or the best answer because the only perfect algorithms that we know for those problems take a really, really long time. For example, let's say we want a program that would determine the most efficient route for a truck that delivers packages, starting and ending the day at a depot. It would take weeks to run, going through all the possibilities. But if we're okay with a program that would determine a route that's good, but maybe not the best, then it could run in seconds. In some case, good is good enough. How do you measure the efficiency of an algorithm? We could time how long it takes to run the code, but that would only tell us about that particular implementation in a certain programming language on a particular computer and just for the input it was given. Instead, computer scientists use a technique called asymptotic analysis, which allows algorithms to be compared independently of the particular programming language or hardware, so that we can conclusively say that yes, some algorithms are more efficient than others. Now, you can learn about algorithms and asymptotic analysis on Khan Academy, thanks to the contribution of two Dartmouth College professors. Tom Corman is the first author of the most popular college algorithms textbook in the world, plus the author of Algorithms.
Okay. So pretty much summarizes where algorithms are pretty much applicable, right? And as you could see, well, you could be able to apply it everywhere, right? From the moment you get up until the time that you actually sleep, right? So let's go to our task, which was what? All about sorting algorithms, right? Okay, so we actually learned that sorting is just arranging data in either ascending or descending order, and that it actually makes searching easier as well. Okay, now these are the common sorting algorithms, and pretty much we actually talked about bubble sort yesterday. So it's your turn as a group to actually present the algorithms that was tasked for you to do, right? Like insertion sort, selection sort, quick sort, merge sort, and deep sort. But, oh yeah, I'm opening a different slide. This doesn't show which groups actually work on which. However, you do know which group you belong to and which sorting algorithm you actually worked on, right? Okay, so we start off with insertion sort. Okay, most likely this is what? FL1 and FL3, right? 1 and 3? Okay, regardless, let's start off with, okay, there are 9 groups, right? So we start off with FL1. And then we progress all the way to FL9. That should be the easiest way. However, stop sharing. Okay, guys. Could you, okay, everyone's allowed to share screen, so no problem. Okay, so we start off with the representative of FL1. May I know who the representative of FL1 is?
Recording in progress.
Anyone? Oh, this is really annoying. If
Hi,
FL
hello. I'm not the FL, but I'm like one the member of the group.
Christopher, you sound like a. Oh no, it's not.
Wait, I'm Stephanie.
Okay, Stephanie. Sorry. Let me just pin you, yeah. Steph, you're gonna be presenting.
I think all of us will present like, yeah.
Okay. Yala, let's just make the. Okay. So
Okay,
regardless, you may start.
okay. Kevin, can you share the screen?
Can you guys see my screen?
Yep.
Okay.
Could you go to presentation mode so it's gonna be bigger? Still not in presentation mode.
Oh, there we go. The option was blocked by the Zoom overlay.
Okay. Right.
So hello everyone. I'm Gervasius Kevin from Group 1. And we from Group FL1 is gonna present about insertion sort. This group is consisted by me, Stephanie, Daniel, William, Richie, Andrian, and Rehan. So first, what is insertion sort? So the definition is basically it's a sorting mechanism where the sorted array, like an array is a data structure containing a number of data values, and it's built having one item at one item at a time. Okay, so the elements in the array, like let's say there are 1 and 2 and 3 and 4 and 5. So there are 5 elements, and so the array elements are compared with each other sequentially, and then they're arranged simultaneously in some particular order. So, for example, the order is 5, 3, then 4. If we want to sort it from smallest to biggest, so we need to put the smallest number in the most left. So the first element is compared to the second element, and if the second element is smaller than the first, they're going to be swapped, and it's just going to be like that all over. Okay, Rehan, can you explain the advantages and disadvantages?
First of all, the advantage of the instruction it is their simplicity. It also exhibits how to performance while dealing with a small list.
Could you speak louder, Rehan?
Oh, okay.
Are you in Zoom right now? No. Yeah, most likely it's better if you join so that the online students would also be able to hear you. Yep. Okay. Yep. So Rehan will just join the Zoom first so that everyone would be able to hear his explanation. Okay, Kev? Should I call you Kev or Kevin?
Just Kevin, it's fine.
Okay, Kevin. So, Kev. Oh yeah, because of that. Yeah. Oh, okay. Yeah. Turn on your camera so that everyone could see you.
So yeah, the instruction is having the advantage of the
Maybe Sergio can like mute when Rehan is talking.
Yep.
Maybe.
Okay.
So yeah. Okay. Okay. Uh, the main advantage of the insertion is the simplicity. It also it have a good performance while dealing with a small list. And the space requirement is minimal because they're using the in-place sorting algorithm. But the disadvantage of the insertion is it doesn't perform well like other that having better sorting algorithm. So, and this insertion is do not deal well with a huge list. Therefore, the insertion sort is particularly useful only when sorting a list of few items. That's it, sir.
Thanks, Rehan.
Okay.
Okay, I'm gonna be explain about the algorithm. So insertion sort algorithm is, so you get the array first, and then you're gonna like use for loop to loop over and over again for each element to see if the previous element is bigger or smaller than the second element, which is the initial position of it. And then you compare it over and over again. And then if you want to make it an ascending, it means like, so if you can see from the code, if you want to be ascending, then the j element of the array needs to be bigger than the key, which is the key is like the I element of the array, which is I element is like the second element. So j is like first element, I is like the second element. And then if you want to do ascending, you just descending, I mean, you can just change the operation symbol to smaller than the key, and then it will works just fine. Yeah.
Okay.
We'll talk about the pseudocode. Like Steph said, the algorithm is comparing second and first. So previously there was like the real code, but this is the pseudocode. This is what happening in the code. First, if you see this line, if A is bigger than B, A swap with B. What is swapping is the value of the A and B, but not the variable. So if you can say if A is not bigger than B, there's no swapping. We go to the if B bigger than C, B swap with C. Why we go back to line 1? Because we need to compare it again to the first variable, like C, B and C already swapping values, but we need to check it again. We need to check A and B again. We need to compare again. Same with C and D and E.
So here's an example of insertion sorting. Here we have an array of numbers 8, 7, 5, 9, 1, 6, 2, 4, and 3. Now, the smaller number will go to the left until the smallest number is at the left and the biggest number is at the right. So here in the first slot here, we got 8 and 7. Now, since 8 is bigger than 7, 7 will move to the left and switch places with 8, and 8 will go to the right. And then in the second example, because 5 is smaller than 7 and 8, 5 will go to the far left. Now, because 9 is bigger than 7, 8, it's going to stay in that position, and so on and so forth.
So that's, I think it's the end of our presentation.
Okay, thank you very much. So, yep, pretty much if you're looking at insertion sort, it's just like you trying to play cards, right? When you have your cards or the deck of cards on your hand and you try sorting them, let's say for example, with the same suit and the same, and then you try to do it in like in ascending order. So you're just trying to like pull out one card and then inserting it into the right position, right? Agree with me, Kevin?
Yes, sir.
Okay. So how about the rest of the class? Any questions to the group regarding their discussion on insertion sort? None? So everyone's quiet? Well done. We move on to FL2. Thanks, Kev and group. Okay, FL2. So quiet, yeah?
Okay, so I think I can start.
Arish. So should we call you?
Yes. Hi everyone.
Yes, hello. This is our group, FL2. Our group are going to talk about selection sort. Our group consists of Arish, Kevin, Daryl, me, Bayu, and Kenneth.
Okay.
I'll
Okay,
let
so
my
what is it?
colleague to define it.
Okay, so what is it? So the selection sort is a sorting algorithm that selects the smallest element from an unsorted list in each iteration and places that element at the beginning of the unsorted list. It does that basically by comparing that first element to the other elements until it gets the smallest one and put it at the beginning. So it will, at the end of the sorting, it will then sort the iteration in ascending order until all elements are completely sorted. So in the next slide, we'll have an example of this. So as you can see over here, the first step of this a selection sorting algorithm is to set the first element as minimum. Then when the first element is set as minimum, you can compare it with the second element. And if it's smaller, the second element will become the minimum. And it will continue like that until that element set as minimum is actually the smallest of the series. Then after that, when that element has been set as minimum, it will start from the second element, compare it to the rest of the elements, and it will continue like that until the series is actually in ascending order. So over here we can see, for example, an example of 5 elements. So we have 20, 12, 10, 15, 2. This is the unsorted list on the left. And on the right, after the algorithm has worked, we can see that by swapping the elements until the smallest element is at the beginning, the list is sorted in ascending order. So someone can present this flow chart, kind of. Okay, so I can still continue with that. So like basically, as we can see in this one, the A1, A2, A3, in this one, there are only 3 elements in the list. So A1 would be the first element, and we compare it to the second one to see if it's a minimum or not. And if yes, then compare. If A2 is bigger than A1, then we can start comparing A2 to A3, and then the list will be sorted. And if it's not smaller than if A2 is smaller than A1, then A2 becomes the first of the list. Then A1 will be compared to A3, and then yeah, it goes on. So Daryl can present the advantages, or like why is it used for?
Absolutely, you just give me the opportunity right now. Why is selection sort utilized? That's an interesting question. It organizes everything quickly when a list contains a number of elements. So as a, sorry, who was the one narrating earlier? So basically, as explained earlier, we have several different elements of varying numbers or values, and then the selection sort is utilized to organize all those different elements, those different elements into either ascending or descending, whatever. It uses a lot less memory space and it swaps everything all at once, and then it sorts and I'm sorry, only in ascending order, not descending. It sorts. So essentially, it organizes everything that is already sorted. It's a useful algorithm when it comes to it's rather difficult for me to explain that, but you know what I'm saying, right?
Go ahead, Daryl. Explain it.
Basically, based on what Arish said, it sorts everything or organizes everything to ascending order, and it uses less memory space.
Okay.
Sorry if I'm not too specific with my statement over there, but yeah, it's a good try, isn't it?
No worries, Daryl. It's okay. Hi, guys.
Thanks.
Yep. So at least we know that, okay, we use selection sort if there's not much data to work on. And the items that are in that list is already like almost pre-sorted, right? Because yep, it's what it says on your slides eventually. And yeah, I just would like to correct you that it just doesn't sort in ascending order. Pretty much it could be able to sort in descending order as well.
I'm sorry, that's what I stated earlier, Mr. Jude.
Okay.
Yeah, but yeah, I made a mistake.
Okay, no problem there. Thanks. Anything else?
No, this is the presentation. Thank you. And if you have any questions, yes.
Okay, thanks, Arish. Not unless the class has questions for FL2 or group 2. None? Okay, thanks. Thank you very much. Group 2. We move on to group 3. Who's in group 3? No one?
I am, sir.
Okay, Randy.
Wait, sir. Yeah.
I share the screen. Okay.
Hello, everyone. I'm from group 3. Our group gonna present about insertion sort. My group consists of Sandrian, Hikari, Kimi, Ferdinand, Pandia, and Maria.
Go ahead, Ren.
All right, so the first thing is how it developed and came to be. the first one that came up with the idea was Donald Shell. He made substantial improvements to the algorithm and modified it and first called it a shell sort. This is done by comparing the elements separated by a distance that decreases on each pass. Until then, in 2016, Bender, Martin Farash Colton, and Mysterio published a new variant called the insertion sort, which is the sorting method that we know now.
Nicholas, you're muted.
Yeah, that's all I had to say really. It's how it came to be. So it went from a simple algorithm and it got developed into the insertion sort method that we know now. And that's about it from me.
All right, I'll be explaining how does it work. So in insertion sort, there are an array of elements. In this example, their values. They're divided into two groups, the sorted and unsorted. So the way it checks, so it checks the unsorted value if it's greater or less than, and it will sort itself depending on how big the number is. So say in the example, we have 3 and 4 in line 2. 3 is less than 4. So then it sorts itself by moving it behind 4. And now we have a fixed. In the middle of the array, for example, what differs this from other sorting algorithms is that not only does it check the predecessor behind the unsorted, but he keeps on checking just literally everything behind it. So say in line 5 of the example in the image, we have the value 1. Of course, it's less than everything else behind it, like 12, 10, 4, 3, 2. It keeps checking that. And then depending on its position, of course, it sorts itself to the correct position, like right away. And then it keeps doing that. And then we have the end result, which is it's the sorted position. Right, next is pseudocode. Thank you.
Okay, so for the pseudocode, there's a line which is called insertion sort A. A representing the array right there. Wait a minute. So the A is representing the array, which is the number in the group. And the next line is the I, which is 10 for variable, is always start with number 1. 2 n minus 1, n is 10 for array length, which is how many number are there in the array. And the next line is p equals to I. So p representing the position, and it's same with the I. And next we will continuing to the condition. This condition will if this condition are true, it will continuing to the loop. The condition are if the position are greater than 0 and the number of array inside position minus 1 is greater than the C, which is the current number in the array. So in the loop, there's array P equals to array P minus 1. So if these two conditions are correct, the array P will be replaced by array P minus 1. And the position equals to position minus 1. So the position will be minus by 1 every time it's true. Continuing to the last line is the array P will be replaced by the current number. So for example, I have number 3, number 5, and number 1 right here. So the I will always start with number 1. And the current number inside the I, so this is the I. And the number inside is 5. So the current number is 5. And the P is always equal with I. The I is 1, so the position is 1. After this, we'll continuing to the condition. The P is greater than 0, which is correct. And the array P minus 1, so P minus 1 is 0. So this is array P minus 1, which is 3, must be greater than the current number, which is 5, and it's wrong. If it's wrong, we will skip to the last line, which is array P, this is P, will be replaced by the current number, which is 5. So basically, So basically, we will replace this number 5 with the number 5. So it changed nothing. For the next step, it will continue to n minus 1, which is 3 minus 1 is 2. So we'll continuing to the number 2. So the I will be in number 2. And the current number will be changed into this number 1. And the P will also change into 2. And we'll continuing to the condition. The P is greater than 0, which is correct. And the array P minus 1, which is 5, is greater than the current number, which is also correct. So the array P will be replaced by array P minus 1. So this number 1 will be replaced by number 5. And the P will be minus 1. So it will be 1 right here. And the array P, if this is correct, we'll continuing back to the condition. Is it the position still greater than 0 and the array P minus 1 is still greater than the current number? If it's correct, we'll continuing to this to the loop, which is AP will be replaced by AP minus 1. So this 5 will be replaced with 3. And P will be minus with 1. So this is 0. Sorry. And back to the condition, 0 is not greater than 0. So it's wrong. And we'll skip to the last line of the code, which is array position will be replaced with the current number, which is 1. So basically, we are sorting the number into the correct order. That's it for the pseudocode. Next.
Next thing we have the flowchart. So at first, we will start with two lists or two array. The first one will be the unsorted list, and the second one will be the one for the correct one. We're gonna call the unsorted one n and the correct one I. And then so we will take the first array from n or n1. We will insert that to I. So n1 will turns to I1, and then the other array in I will be shifted if there's an array in I. If there's not, then the n will just turn into I1. Okay, so after that, we're gonna delete n1, the old n1, and then n2 will move back to n1 and so on. And after that, the algorithm will check if I1 is less than I2. If I1 is less than I2, then we will go back to check if the n list is empty. If it's not empty, we will go back, repeat the process again. If it's not empty, if it's empty, they will print what's the final I list is. And then if I1 is greater than I2, they will swap position. So I1 and I2 will swap position. And then the process will continue for I2, I3, and so on. Next.
Okay, so this is the advantages of insertion sort. Basically, the first part is that it's a simple algorithm. As we talked about before, it's very similar to playing cards. So it's easy and straightforward compared to other sort methods. The second is that it is efficient with small data sets, especially if the elements are already close to being sorted. So it takes a very short time. And if the elements are already completely sorted, it will not waste time in like useless operations. So the runtime is 0. It has a stable sorting technique. This basically means that it maintains the position of 2 equal elements relative to one another. So this is needed when the equal elements are distinguishable. For example, if it's not distinguishable, it'll be like 2 of the same number. So the array would be 7, 8, 9, 9, 10. The 9 are interchangeable, so it won't be like, it's not really useful for it. But indistinguishable, it'll be like, for example, 2 kids with the same name but separated in different classes. So if you were to make an alphabetical list of the classes, if there's no stable sorting technique, it would mix up the classes, but it will still be alphabetical. While with the stable sorting technique, it will be like alphabetical class list of class A and then alphabetical classes of class B. So it separates it. It sorts the elements as soon as it receives them. This is basically because it's an online sorting algorithm. So this means that it'll work if the element is provided one at a time. So it processes it serially. So the algorithm sorts as the elements are added in. So it doesn't need all the elements available from the start. Space requirement is minimal. This is because it does in-place sorting. Basically, the algorithm sorts it in the same place. So it produces an output in the same memory that contains the data by transforming it. There's usually an additional memory allowed for the variables, but the additional memory doesn't really change, even if the number of elements change. Next.
With the disadvantages of the insertion sort, there's actually not very much disadvantage. There's only one main disadvantage, which is that insertion sort doesn't deal well with a huge list. This is because it requires n squared steps for every n elements to be sorted. So the larger the number of variables to sort, the longer it's going to take, and therefore it is particularly useful only when sorting a list of few items. So the option to use the insertion sort is basically only when you have a few items, and when you have too much items to sort, it will take a very long time. Therefore, that is the very big disadvantage of the insertion sort. Next.
And then?
So that's the end of our presentation. This is our context, and thank you very much for paying attention.
Okay, thank you very much. This is just the third group, right? Nice. Okay, well done so far. We now move on to the fourth group. So maybe by now you actually know why people came up with different algorithms to sort data, right? Because it's what, how do we say it? Yeah, per case-to-case basis. Got it? So if you're just working with small amounts of data, then this specific algorithm actually works better compared to the other algorithms, right? Okay, group 4.
Hey, Sir Jude. I'll be presenting for group 4.
Okay,
Arvin,
Jess.
can you please share the screen?
Were you with us yesterday, Jess?
Yes, sir. I wish I could have been on site today.
Okay, go ahead. Yeah, it's easier to present online than on site, right?
I think we're experiencing some difficulties. Okay.
Okay.
So this is our minimalist presentation, not because it was rushed. And we are from group 4 and we'll be presenting the selection sort. My colleague will be explaining how it works. Arvin, can you please?
Selection sorts, basically in it, you will be dividing the values into 2 sections, and you'll normally put the ones you have sorted on the left side, which is basically the smallest number value. And the further you go to the right, it will get higher.
So the pros and cons of selection sort is that the advantage that it doesn't depend on the initial arrangement of the data. So you can just scan the entire array and then just does it repeatedly and finds the minimum value. And also it's light on memory usage. It's not very costly when it comes to memory, right? The disadvantage is that it's unsuitable for large data sets because it takes a long time with large data sets because it maintains 2 subarrays.
So here we'll be going through a walkthrough of the selection sort, like in person. So here we have an array of numbers from 1 to 8 that we have to sort. Basically, how the selection sort works is that the computer can only look at each element of the array, one element of the array at a time. So we're going to start from the left, from the far left of the array, working our way all the way to the right, looking at each element one at a time. Storing the smallest number in a temporary memory. Basically, looking at 6, that is our the smallest number that we've seen so far. And moving on to the 3, as 3 is less than 6, we're going to store that temporarily as the smallest number. Moving on to the 8, as 8 is bigger than 3, we're going to move on to the next element, which is 5. Arvin, not yet, which is 5. Which is still larger than 3, so we're going to move on to the next element, number 2, which is less than 3, so we are going to temporarily store that into our memory as the smallest element. Moving on, 7 and 4, and finally 1, which is the smallest number that we've seen so far. Taking that, we're going to swap the number with our first element, and 6 is going to take its place. Basically, that's a rundown of how it works, and the algorithm is going to repeat itself until all of the numbers have been sorted. So like, it would be a hassle to do it one more time, but basically the computer would look through the rest of the array starting from 3, the second index all the way to 6, and we can find out that number 2 is the smallest number of the array. So taking that, we're going to swap it with the into the second index of the array. The list goes on and on until the list is sorted, until the entire element is sorted. Yeah, you can just skip that, Arvin. Thank you. Next slide. You're doing this slide. So basically a rundown of the algorithm. Arvin, can you please go to the next slide? So basically here's the rundown of the algorithm. For I from 0 equals n to I, here we set the counter I as 0, and then we move up each element, each incrementing by 1, all the way to n minus 1. The next line chooses the smallest element of each array, and then we swap that smallest element as we did with the ith item. Yeah, that's it. Next, please. So here's a visualization of the sorting algorithm. Arvin, you gotta set it to sort selection at the top left. Do you see bubble sort? Next to bubble sort, there's SEL. Yeah, that one. Yeah. And can you please click sort at the top, bottom left? Yes. Thank you. So here's the very slow visualization of the sorting algorithm. Selection algorithm. It basically selects the smallest element of the array from the counter and placing it into the left side of the array. Yeah, that's it. Can you please go back to the slide, Arvin? Thank you. Now evaluating the sorting, this selection sort algorithm in terms of memory and time, as Sergio discussed yesterday. This algorithm requires a temporary memory of one element to store the smallest element of the array temporarily. As for the running time, as you can see or feel, it is painstakingly slow to arrange the array of 8 elements. It can be denoted by the function capital O of n squared, as you can see in the next slide. Right here. And as for the worst case scenario, it is also denoted by the O of n squared. So therefore, it requires n number of steps to get n elements to be sorted. Therefore, it takes quite a long time to sort, and usually it's used for very small arrays, as the steps increase exponentially as the number of elements increase. Thank you. That is it from me.
Okay, you're the only one presenting. The rest are like support cast,
And
right?
Arvin. And
Okay.
Arvin.
Oh yeah. Forgot. Where was I? I was just here. Okay. So thank you very much. Well done.
Thank you, Sajid.
Right. Okay. So we look and move into the next group. Group 5.
Okay, so my group is going to present. Let me share screen first.
Okay, Tiff.
Hold up, give me a moment. Okay, can everyone see the slide?
Yep.
All right. I think it's good morning now, right? Okay, good afternoon, everyone. Today my group team and I are going to present what we know about quicksort so far. So first off, to explain what quicksort is, this will be given to, yeah. Go ahead. Whoever's going to explain.
Can you hear me?
Yeah.
Hello?
Okay. What is quicksort? Quicksort is a divide and conquer sorting algorithm. It takes a sorting array and breaks it down into subarrays, which are in turn broken down into more subarrays. This is achieved by picking an element as a pivot, whether it be at the far left or by the far right, or even in the middle, and partitions the given array around the pivot. This type of sorting algorithm is developed by a British computer scientist named Tony Hoare in 1959. An example of the application of quicksort includes commercial computing, which is used in various government and private organizations for the purpose of sorting files by name, date, price, and etc. And next.
So now I'll be attempting to explain what quicksort works, but before we get onto the pseudocode, like I think it's easier for people to digest information with some visuals. So to begin arranging, you must first select an element as a pivot, and a pivot is basically a splitting value, and you'll understand what I mean when I go through this. So there's actually ways to also select a pivot, but in this case, the example has chosen the value at the rightmost. So like number 2. So to rearrange the array, you compare the pivot to the rest of the elements, and it's important that you start from the leftmost index. You want to find firstly an element that's greater than the pivot, and secondly, an element that's smaller than the pivot. So, and again, it's crucial that you do this in order. So greater first and then smaller, and starting from the left. So again, in this example, 8 is the first number from the left that's bigger than 2, and 1 is the first number on the left that's smaller than 2. So once you've determined these values, you just simply switch the positions, and you repeat this process and rearrange the numbers such that the values on the left are smaller than the pivot and the values on the right are bigger than the pivot. So in the last array, as you can see, 1 and 0, although not in order, is smaller than 2, and vice versa. And if you also notice, 2 is basically already in its correct position and in the correct sorted position. So if that means it's indication that you're doing the sorting correctly. So you can go next.
Oh, hold on.
Okay, so next we have recursion, and recursion is basically just repeating the partitioning part after the pivot point has been moved into the sorted position. So we do it for the unsorted arrays, which is the one on the left side of the pivot and the right side of the pivot. As we can see, 1 and 0 is not sorted yet, so we need to apply the partitioning process again. So 1 is bigger than 2, is greater than 2, and 0 is smaller than 2, so we switch. And the same is also done for the right section. But it's done from the right to the left, right?
Okay, so summing up what this quicksort algorithm does is it picks any element as a pivot and then partition the array on the basis of the pivot. And then the last step is to apply quicksort on both left and right position repetitively and also separately. So it keeps repeating until it's rearranged correctly.
Okay, next up, I'm going to be explaining about the pseudocode. So there are important terms you need to know before we get to this, which I'll be explaining in the next slide. But pretty much the low, or you can say the starting index. So the index is pretty much the position of the integer or the numbers. And the low is usually located to the most left, and here the high, or you can say like the n, is located at the very right. And here is an example of a quicksort, the pseudocode for normal quicksort. And because then here we also have the pseudocode for the partitioning, where you also have the array, which stands for A. There's the position for start and end. And to explain more about this, I have taken an example from a YouTube video I watched, which I'll be linking down the reference list. Here, to start off, we will start from this image here. I think I need to use my, to annotate. I don't know if this works. Okay, wait. Is it blocking? Wait, can you guys see my cursor? It's just a pointer like this. No, yeah.
Yep, we could.
Oh, we can?
Yep.
Okay. I can't see what's above here now, but pretty much. So first we start off to determine the pivot, right? And most of the time, yeah, you start from here. What's it called? No, not most of the time, but most professionals. Okay, so they usually take the last, and the array is pretty much like the value. So here the value is 0, and so this is our pivot. And R just means right, or N, which is to the most right. And here it says that I equals to L minus 1. So L is pretty much minus 2, not minus 2, but 0, because this is the position. So it's 0. And if you do minus 1, you'll pretty much go here. So this is where I is. And now for J, we will start from L up to R minus 1. So L is here, right? And you'll be shifting this J up until minus 1, which is minus 3. Oh, whoops, right here. Okay. Now we go to if the value of J or the array of J is less than the pivot itself. So let's say here, the value here is minus 2, right? It's less. Because it's less, then the I will be plus 1. So I plus is pretty much just plus 1 as a position. So that's why, therefore, the J and the I are located both at the same integer. And here we can see, how should I say, swap are the value of I and the value of J. So before that, we need to move again to the next tree. We have to check if this is less than the pivot or not. And unfortunately, well, 3 is it is not less than the pivot, so we can move on to the next one, which is minus 1. And because minus 1 is less than the pivot, the value, the array, you can do another plus 1 here. So the I will be here now. And you can swap these two, which will turn into the value of I, the value of J, can swap it. And pretty much there'll be like loops. It's recursive. So in the end, after swapping, you will end up with something like this. Because yeah, you have to move the pivot you have to move the 0 and the 5. You swap them together, and then you can go back and return to I plus 1. And here's the implementation of the for Python. So basically, pseudocode and programming code is different stuff. Like pseudocode is not a programming code. That needs to be understood. So yeah, here is the Python version. And now someone is going to explain about the advantages and disadvantages.
Yes. Sorry. Oh, okay. Let's just mute it. Moment.
Who's gonna do last slide? Just now.
It's me.
Okay.
So the advantages. It's in place since it uses only a small auxiliary stack. So it has a fixed and a small storage for the coding, and it only requires nlog and time to sort items. It also has like extremely short inner loop. So by using this sort type, it's more efficient. It's been subjected that it's a thorough mathematical analysis. And there are also some sorting types that can't deal with a huge list of items, but with quick sort types, we are able to deal well with a huge list of items. As for the disadvantages, quick sort is actually very recursive, so it loops, and loops again. And it also requires a quadratic in the worst case. It's also very fragile, so a simple mistake can go by unnoticed and just ruins the whole program.
Okay, so I guess that's the end of the presentation. Here's our references if anyone is interested and to learn from. So yeah, thank you.
Okay, that's it. I guess there's a couple of questions on the chat box. Bernard has one. Steph also has one. So I do suggest some members of the group give any answers to these questions.
So I've already answered Steph's question.
Okay. Any element or the last element? Okay.
Yeah. So there's ways to strategically choose it, like randomly, or like I think they do it from like middle. But the example that we use, they just chose the rightmost index.
Yep. Okay. And a while back, a demo from one of your classmates as well. They use the pivot as the center, right? So it's pretty much case-to-case basis. But choosing the middle point as the index is actually good, because after the first iteration, you already know that on the left of the pivot, all values are less than, and on the right of the pivot, all values are greater than the value of the pivot. So it's pretty much makes quicksort a little bit more efficient that way. Okay, but yeah, regardless, we have the freedom to choose the pivot point actually, and it has its own advantages and disadvantages as well. Okay, good. Thank you very much. We now move on to the next group. Group 6, or is it 5? 6. Okay, 6 it is. So I need to change. You're presenting, right? Okay.
Hello, sir. Is my screen visible?
Yep, it is.
Okay, so good afternoon to all students and also to Sir Jude. I hope you all are doing well today. My name is Joshua, accompanied by my friends Farik, Rachel, Raisa, and Owen. We are from group ASN 066, and today we are going to discuss about quicksort algorithm. But first, before we discuss further about quicksort, let's look at the table of contents so we can have a bigger picture of what we are going to discuss and learn today. First, we are going to learn about the definition and background. Here we are going to learn a bit of history about quicksort algorithm itself, as well as its formula. Next, we will be discussing and learning more about the implementation. Here we are going to learn what is quicksort used for, as well as its advantages and disadvantages. Next, we are going to have a simple study case so we all can understand better about how to use quicksort algorithm. For the definition and background, it would be explained by Raisa.
Okay.
Yeah. Okay.
So I'm going to talk about the history of the background of the quicksort. So it was developed in 1959 by a British computer scientist, Tony Hoare. Quicksort is a recursive divide and conquer algorithm that is ranked as fastest in its class. Its boasts of an average time complexity of O and log n in big O notation, which compared to its peers, it's pretty fast. And big O notation is a way of measuring how well an algorithm scales or performs as amount of data, it process grows.
Okay, so in the implementation of quicksort algorithms, we ask the question, what is quicksort used for? Well, it's basically used to separate lists of elements into two parts and then sort each part recursively. Or in other words, it implements a divide and conquer strategy. And of course, as it's one of its major upsides, being its efficiency, people will use this for a variety of different things, basically sorting things like ranging items, ranging prices, or even sorting catalogs. So it's basically probably one of the more mainstream used sorting algorithms out there, because it's like the previous slide said, one of the class leading sorting algorithms, because it's efficient and easier, I guess. Next slide.
So next we will be discussing about the disadvantages of quicksort algorithms. First, its worst case performance is similar to average performances of the bubble, insertion or selection sorts, but do not fear too much, as this is just a slight disadvantage. Next, in general, the quicksort produces the most effective and widely used method of sorting a list of any item size. Okay, next.
So here is one of the examples of quicksort algorithms. First of all, there are 8 random numbers in the array which are not in order. And in programming, these elements are called index, which is the first element is equal to index 0. So in total, there are 8 elements, and the last element is index 7. So the first step of quicksort is to set a pivot element, which is the mark to be the comparison between the numbers later. Usually the pivot, to make the code easier, the pivot is the most left or right of all the elements, or the first or the last element in the array, but you can freely choose any number of in the array. In this example, the pivot is number 5, which is the first element of the array. Then we select the left pointer, which is the first element, and the right pointer, which is the last element after the pivot. From here, the program will compare the pivot and the pointers with a sorting condition. So if the left element is less than the pivot, it will stay on the left-hand side. And if the right element is greater than the pivot, it will stay on the right-hand side. So in the example, 3 is less than 5 and 7 is greater than 5, so they both stayed in their place. Then we move closer to the center whilst comparing both of the numbers. Now, on the other hand, if neither of the element matches the condition, both elements will be swapped. So if the left element is greater than the pivot, and the right element is less than the pivot, both of them will get swapped. So as you can see here, the number 8 and number 2 will be swapped because 2 should be less than 5 and 8 should be greater than 5. Then the program will keep looping and repeating the orders and conditions until both left and right pointers are stopped on a certain point, which the numbers no longer match the condition. Okay, next.
So in the picture here, the left and right. Okay, the left and right pivot. in the picture before, the left and right pivots have stopped. And in the left and right pivot, in the last picture, the left and right pivot has stopped, and the left is greater than the right, so we need to swap the pivot and the right pointer. And then in the next one, we can already see that in the left hand side of the pivot are all smaller numbers in the pivot, and on the right hand side it's all bigger numbers in the pivot. So from here we'll create two sublists, for one on the right and one on the left, and then we repeat the process we did before and until we end up with an arranged list.
This is a little description of the pseudocode for the quicksort method. Yeah, pretty self-explanatory here, I guess. So yeah, it's all I can say about the pseudocode then. Yeah.
So thank you everyone for listening to our presentation about quicksort algorithms. We're sorry for if we have any mistakes, and I hope you guys enjoyed and find it informative. And don't forget to stay hungry and stay foolish, so we all can be a lifelong learner. And here are our references in case you guys are interested. And once more, thank you for listening to our presentation.
Thanks, Josh and group. Well done. Yep, that's the important thing, right? We have to be hungry, as always, for knowledge, that is. Although it's already past 12, I know it's not just for knowledge that we're hungry on, but also, of course, food as well. But it has to wait. We still have like 2 groups to present. Sorry, 3. Okay, so let's get it done. Who's next? Group 8? Or I'm sorry, 7.
I think I'm next. Hello? Hello?
Yeah, we can hear.
All right. So hello everyone, my name is Peter and I'll be co-presenting with Philbert on merge sorting. Okay, so let's start.
Your group?
Group 7. We are part of group 7. Can you move on, Philip? I mean Philbert.
Philbert, can you next slide? Thank you.
All right, so what is merge sorting? Merge sorting is basically a divide and conquer type algorithm, and it was developed by John von Neumann in 1945. And what it does is that it splits one array into 2 subarrays that will then be split again until there's only one element in each subarray. Then the algorithm will run the process to piece the subarrays back together in a way where the end result will be an array with the elements in order. All right, next up, let's go into the pseudocode explanation, and I'll pass the role over to Philbert for now.
Oh, okay. Hello?
Yeah, we can hear you.
Okay. Basically the pseudocode is like well from the beginning, let's just say that n is the length and then a is the array. So if n is the variable, it's compared to 1, then return to a, so return to the beginning. However, if it's not 1, then this else command will make it into Like for example, this one, we'll just from the beginning, the else command will divide it into two, and then it will divide it again and go on and on. And then at the bottom, return merge is so end the sequence. And then after the whole thing is divided, we'll just we'll begin the merge procedure. Is if a well, first let's just say that in the bottom right you'll see that the A, B, and C. Let's imagine that we'll tag their names as A, B, and C. So if A is greater than B, then B is add to C, and remove the B. And then after that, add A to the C. Or however, if A is smaller than B, then the if command will not activate and do the next while command. That is put A on C and then put B at C. And then it loops to the back loops all over again until it do the last part, that is doing the merge at the bottom. I guess that is a brief explanatory from me. I'll pass it over.
All right. So what are the disadvantages and advantages of merge sorting? So one of them is that it's really effective when dealing with a really long list of data, but when dealing with shorter lists, it will be less effective, as it would likely be faster to use a different method. And another disadvantage of merge sorting is that it will keep merge sorting arrays that have already been sorted, and this will most likely lengthen the process. All right, and so with that, I conclude this presentation. Thank you for listening, guys.
Okay, thank you very much. It's as long as recursion is actually involved in the discussion, everything seems to be quite difficult to understand, right? So it's normal. Yeah, there are some problems that we could solve using different ways of designing the algorithm and the program, that is. And yeah, recursion is just one of the ways to it's a programming technique actually that we use, wherein the function actually calls itself, right? And it's most often used for these two algorithms, merge and quick sort. Although you could actually be able to solve it without using recursion. However, it's actually going to be more difficult, right? So we move on to the next two groups, group 8 and finally group 9. You'll be the first one? Okay. So let me change my speaker so that no feedbacks or whatsoever. Go ahead.
Okay, so good morning. Good afternoon, Sujit and guys. So we are from group 8. There's Albert, Alvin, Bernard, Chelsea, Wilbert, and me. And we will discuss about merge sort. For the outline, we'll have the background definition and of course the pseudocode. For the background, I'll leave it to Chelsea.
I'm going to start off by giving a brief overview about the background of merge sort algorithm. It was invented by John von Neumann in 1945. In 1945, John von Neumann, the Hungarian mathematician, physicist, and computer scientist, developed the merge sort algorithm. Merge sort is a general-purpose sorting method that uses a divide-and-conquer approach. It was developed to address weaknesses in less efficient algorithms such as the bubble sort. Now I'm going to pass on the next slide to Wilbert, and he'll be explaining the definition.
So the definition of the merge sort is basically it's a sorting algorithm that sequences data by continuously dividing and merging items in the list. So basically every single item in the original unordered list is going to be divided into two groups. So if you see at the picture, we have the four numbers, the 40, 2, 10, and 4. They're going to be divided to 40 and 2, and then 10 and 4. And they're going to be divided again. So the 40 and 2 is going to be divided to 40 and 2. So they are now indivisible. They cannot be separated into 2 again. And then after they are all indivisible, 40 is alone, 2 is alone, 10 alone, 4 is alone, they're gonna be merged together while being sorted in an ascending order. So as you can see, the 4 and the 2 are going to be sorted into 2 and 40 instead of the 40 and 2, and 10 and 4 is gonna be sorted into 4 and 10. And then both of them are now gonna be merged and sorted again, creating the groups of 4, the 2, 4, 10, and 40. Until there's only one list remains, which is the last list. Now I'm gonna pass the pseudocode to Bernard.
To begin executing the algorithm, we must first initialize the array and enter numbers into that array. Then we initialize the merge sort function. And next we find the midpoint of the array by dividing the array length by 2. And then we round it up with the ceiling function. Next, we divide the array by the midpoint into 2 halves, array 1 and array 2. We then call merge sort on array 1 and array 2. Then we compare elements of array 1 to array 2. And next, we insert the smaller element from the comparison made into a new empty array. And we repeat this process until both array 1 and array 2 are empty. Finally, we return the final complete array as the output. Next.
So that concludes the presentation. If you have any questions, you can ask.
Okay, guys, are there any questions? Albert's actually waiting for questions. None? No questions? Okay, so thank you very much. Well done. I do appreciate for everyone who actually presented. Seems that you have a well grasp, very good grasp actually of the terms. Then very good understanding as well of how you actually trace and simulate the algorithms. Okay, it's very good. It actually makes my life easier when we start our class next week. Okay, so right, let's move on to the last group. Group 9.
Good morning, Mr.
Hello, Brian.
Yeah, so today we're gonna present about the heap sorting algorithm. So if who's presenting slide 1? So if the person who's presenting slide 1 would like to start.
Yeah, next slide. Okay, so what is heap sorting algorithm? Is a type of efficient sorting algorithm that uses comparison-based sorting technique. It visualizes the elements of the array and arranges it into a special tree-based data structure called the binary tree. And heap is also known to be an improved version of this binary tree because it adjusts the position of the elements in the array. So how does it adjust the position of the elements? It creates a min heap or max heap to process the elements. Min heap or max heap presents the order of the array, identifying which root element is the minimum or maximum element of the array. Each root of heap is deleted and stored to a sorted array. Within each step, this process continuously repeats itself for the remaining elements. Now, we run a function called heapify on all the non-leaf elements of the heap in a complete binary tree. Heapify is to modify it to become a maxed or min heap. Yeah, next slide.
Right. So heap sort can be used in the real world in the form of administration. For example, in SIM card stores, heap sort can be used to sort customers who have to pay bills first so they can be dealt with more quickly. Another example comes from Glenn Raid, a former employee in Bell Canada. If you guys don't know what Bell Canada is a telecommunications company. So he was tasked to improve a program that transferred data like on a network. The original program used 30 minutes of CPU time to run. So Glenn Raid was tasked to like optimize and improve the system so it would run quicker. So it would use less CPU time to run. Since the original program used 30 minutes of CPU time because it ran on sparse arrays, which basically requires the data to traverse a lot of code to like process. So by moving the data to a heap, Glenn was able to improve the CPU time from 30 minutes to like a whopping 30 seconds. So in short, heap sorting allows programs to sort data in a very efficient, quick, and optimized manner.
For the example of a sort of a heap sort situation, on the left, we have the input numbers over here. These are the numbers that we are gonna try to sort. First of all, what you have to do is create a heap array, which is this. Now, what you notice is that they are still unsorted yet. Well, 16 is still in the middle, and 2 is still like randomly. The way a computer sort a heap algorithm is by having a parent node be always bigger than the node below it. So in this case, 16 is our parent node, and so below it can be the other numbers. And after this, what the computer does, we know 16 is the biggest number, so it will simply move it to its final location, number 1 over here. And then after that, since 16 has been moved away, the computer will take usually indices number 4, which is this one, and put it as the parent node on top of here. But the issue, if we keep it like this, is that 9 is a bigger number than 8. So what it does is it simply swaps 9 and 8 around, becoming like this. Which afterwards, the computer will simply see the data, see that 9 is the biggest number out of all of them, put it into the number, being put into the array, becoming number 2. And then number 8 will move up, and then it will see that 8 is also bigger than 5 and 2, which will be the next number in the list. And then do it repeatedly until the 5 and the 2 are sorted into the array.
All right, so one of the ways that we can use heap sort algorithm is by using separate heap and add all elements to it. And we can optimize it by using in-place sorting. We use the array to be sorted as a heap rather than using additional memory for a heap.
Presentation. Thank you for listening to us.
Okay, thank you very much. So guys, if you were actually looking at the different sorting algorithms, most of which actually just implemented a very simple list or an array. right? But for group 9, they actually made use of a different data structure, which is what we call a heap. Okay, so it's actually one way for us to represent data in the computer. And the heap actually looks like a binary search tree, or a binary tree as they call it. Sooner or later, you're gonna be learning more of this. So there's actually no need to worry about what a heap is or what a tree is, for example. You'll all be actually getting more knowledge about this once you advance into the courses that you'll be taking. Okay, so but kudos to you guys. At least you were able to learn something new, right? And hopefully this helps you out, yeah, once you progress in your classes. Okay, so yep, it's almost 12:40, and so maybe I could call on the FLs. Where are the FLs? Yeah, or they went for lunch already. Hey, Bentley's here.
Maybe, sir.
So, are we done or are we done? We're good? There's a question from Arvin. Yep, Arvin. So documentation time. What do you mean by documentation time?
Perlu dokum nggak ya? Bentley.
Mau dokum.
Ya boleh lah.
Ayo guys, on cam.
You're eating, right, Ben?
No, I ate like 20 minutes ago.
Good for you. We're all starving here, so we're all good, right?
Kan I off cam, sir.
Yeah, I know. Okay, so we're all good. We close the session and
take photo.
Photo? Okay, go ahead, take photo lah.
Ayo guys.
Turn on your cameras. And for those who are did everyone join Zoom? Yes. Okay, we're good then.
Okay, 3, 2, 1. Page 2. 1, 2, 3. Page 3, 1, 2, 3. Okay, thank you guys.
Young already, yeah. Okay, so thank you very much, and I'll see you guys next week.